Welcome to another physics video. Today we're going to be reviewing some key ideas of position, velocity, and acceleration. The key thing will be differentiating velocity versus acceleration, making sure that's set. On a fast-moving train, it's not really the velocity that you're feeling. It's the acceleration from the bumps up and down. If it were perfectly smooth, you wouldn't be able to tell if the train were moving or not. The faster you go, the bumps are going to be bumpier, but it's really an acceleration thing, not a velocity thing. So let's practice some graphing now.
So often people get confused because the same pattern means different things on the different graphs. So first we're going to take this flat linear pattern and see what the difference is between position versus time, velocity versus time, and acceleration versus time. Okay, so we had a flat graph, positive acceleration of 6 on it. So what does that mean depending on position versus time, velocity versus time, or acceleration versus time? Position versus time is pretty straightforward. Let's say I'll make somewhere around here a position of 0, and I'll make that the positive direction. The train just sits there at 6, stays the whole time. Now, let's say it's velocity versus time. It's velocity versus time. We don't know where the train starts, but we know that it's got a constant velocity of 6 in the positive direction. Now, if it's an acceleration versus time graph, there's a couple things depending on what the starting velocity was. There's some chance that the train is speeding up in the positive direction, so faster and faster. But it's also possible that the train started out going the other direction in the negative direction and just has a positive acceleration. In that case, the train would be slowing down. Starts out really fast, and then steadily comes to rest due to the positive acceleration. So same pattern in all three, but very, very different things that are happening. Okay, so now we've got something that's still linear, but with a non-zero slope. And this one looks like it starts at -4, goes to 0, and then goes up to +4 over the course of 8. And let's see what that means over the context of a couple different graphs. So let's see if we can predict what's going to happen from that graph using this train. And maybe this would be a good chance to pause the video right now and see if you can predict it for yourself, and then I'll do it. So I'll give you a chance to pause. Okay, hopefully we're back. This time for position versus time, I'm going to put 0 right here. I'm going to keep that the positive direction. So it starts with an initial position of -4, and then steadily, constant velocity travels to 0 and past 0, going the same positive direction the whole time. And the slope of our graph is equal to that constant velocity as it traveled back and forth. All right, let's think about if that was a velocity graph. So if it was a velocity graph, it starts out with a velocity that's -4. And then it's going to slow to rest and then speed up in the opposite direction. And so remember, getting closer to 0 in velocity is always slowing down. Getting farther from 0 is always speeding up. And with that velocity graph, the slope is going to be the constant positive acceleration. One thing you might notice there is that if it's a position versus time graph, then the motion looks somewhat similar to the level velocity versus time graph that we had before. And the velocity versus time graph kind of looked like the level constant acceleration graph, or at least one of the possibilities for the level constant acceleration graph. So you may have noticed that we didn't actually deal with what the sloped acceleration versus time graph would look like in that last thing, and there's a simple reason for that. We're never going to have a changing acceleration during this course. We'll only have flat, constant accelerations of one kind or another. Similarly, for this last batch of graphs that you see up right now, the ones that sort of have the quadratic curve to them, this could only be position versus time graphs. They're never going to be graphs where the velocity is changing in a non-constant way. So let's look at them. We've looked at this on the quiz already, but we've got two graphs. We've got A and C that are traveling in the negative direction, and two graphs, B and D, that are traveling in the positive direction. Now A, if we look at it, we can see that it travels a little bit in the first unit of time, a little bit in the second unit of time, but it just keeps getting bigger and bigger and bigger, suggesting that it's speeding up. Similarly with B, a little bit in the beginning, and then more and more and more per unit of time as you get going, definitely speeding up. The other ones are slowing down. They start out really steep. They've got a steep slope in the beginning for C and D, and then that slope gradually levels off. Similarly, you could look at it and say, it's covering a lot of displacement, a lot of change in position over the first little unit of time, and then less and less as time goes by, also suggesting that things slow down. And so we'd only expect to see these on a position versus time graph. Alright everybody, I hope that was helpful, and remember, this is something that you can really improve on with practice. Practice making graphs, practice making various kinds of graphs, and always think about what the motion means, be able to visualize the motion physically. Alright, take care, I'll see you soon.